Today I want to talk about what happens to a wire that carries an electric current while it's in a magnetic field, right? We know that an electric current will generate its own magnetic field. But if we have what we call an external magnetic field, a magnetic field that was already there, caused by the earth or caused by bar magnets or caused by something else, what happens? Well, there's going to be an interaction between the two. I mean, think about that. You had a magnetic field already there. You've got a new magnetic field that you've generated by the moving electric charges in this wire. In other words, this electric current. There's going to be two magnetic fields, and those two magnetic fields have got to apply a force. They do. They apply a force on each and every electron within that wire, and therefore on the wire itself. We're going to today figure out what that force looks like, and we're going to figure out how to calculate that force as well. But before we do that, we have to define electric current. We loosely know what that means, right? We know that electric current is the movement of electric charge, the movement of electrons in the context of a wire. But more specifically, we would define electric current as the rate of flow of electric charge, right? Anecdotally, electric current is just the movement of charge. But quantifiably, electric current is the rate of flow of charge. That doesn't mean, by the way, how fast the charges are moving. When you're measuring the rate, you're not measuring the speed. You're measuring, rather, how many charges or how many coulombs are flowing per second. If we're standing on the side of the highway with a radar gun, one person has a radar gun like a police officer measuring the speed of the cars as they go by. Another person is standing on the side of the highway counting the number of cars that are going by with a stopwatch measuring the amount of time that it takes. It's the guy with the stopwatch and that is counting that's measuring what's analogous to electric current. The rate of flow of cars, not how fast the cars are moving. Right? You can be standing on the side of a Deerfoot Trail and be measuring the speed of cars to be 130 kilometers per hour. That speed is really high on Deerfoot Trail. But the rate of flow of cars may not be that high if it's 3 o'clock in the morning. There may only be like one car every 4 seconds, right? Difference between speed and rate. Okay, this is what we're talking about here now today with electric current is the rate of flow of charge, not how fast they're going. Now, rate, anything that's a rate has time on the bottom. So if we're talking about the rate of flow of charge, then current is going to be given by the equation Q, charge, over time. Now the symbol for electric current is a capital I. What do you think the units would be? What do you think the units for current are? Take a look up here at the equation. There's a couple sets of units that we can use, one of them staring in the face. Q is measured in, what is it? Coulombs. And T is measured in seconds. So we could say coulombs per second. That works. What also works? You've heard this term before, you just haven't used it. Or at least not correctly. Man, you guys are, it's like you're sleeping here. You guys need to get amped up a bit here to answer this question here. What is it, Blake? Amps, of course it is. Usually we actually abbreviate an amp with just a capital A. Amp is, in itself is an abbreviation, right? An amp stands for, Blake, do you know what that stands for, an amp? Yeah, ampere, yeah. So current, charge over time, because it's the rate of flow of electric charge, and it's measured in coulombs per second, or it's measured in amps. Quick little question here. It's going to go real quickly for us. The question says, calculate the electric current in a wire if this many electrons flow through the wire in 7.5 seconds. Look, we want to find electric current. We're going to say I is equal to Q over T. What's the value of Q? 5.5 times 10 to the 10? No, it's not actually. How would you find the value of Q here? Yeah?
Multiply the amount of electrons by the charge of a single.
Yeah. Just take the number of electrons, 5.50 times 10 to the 10, times the charge of one electron, which is 1.6 times 10 to the minus 19 coulombs. It's actually negative, but as we know, we always drop the sign of the charge there. When we do that, 5.5 times 10 to the 10, 5.5 times 10 to the 10 times 1.6 times 10 to the minus 19, we get 8.8 times 10 to the minus 9 coulombs. All right, now that we've got the charge, let's divide it by the time. 8.8 times 10 to the minus 9 coulombs divided by the time of 7.50 seconds gives us a current of 1.17 times 10 to the minus 9. What are the units? What is it? Yeah, we can say coulombs per second. Anybody else? Blake? Coulombs per second or amps, yeah. I don't care which one you use. Just be familiar with both, because on a quiz or a test sometime, then maybe it gives you one or the other. Even if it's not the one you use, then you've got to be able to recognize that as being a unit for electric current. That's not very hard, eh? Why are we solving for electric current here? Like, haven't we finished the electricity unit? Well, we're solving for electric current here because in a couple minutes, we're going to solve for the magnetic force on this wire. And in order to solve for the magnetic force, we need to be able to understand and calculate the electric current. Okay, because we can't do magnetic force without knowing about electric current. Okay, I'm going to trust that you can solve those problems. Okay. Now, this is the meat of the lesson here today. What's a current carrying conductor? What's a current carrying conductor? What's a simpler word for a current carrying conductor? A wire with an electric current in it. A wire that has a current in it. Fancy names for not fancy things. A current carrying conductor consists of a wire with moving electrons inside the conductor, inside the wire. Now, each of these electrons that move through the magnetic field, each one of them, every single one of them experience a magnetic force. Why? Well, because, remember, they each generate a magnetic field. But now we've got another magnetic field that was already there, caused by magnets or caused by the earth or caused by whatever. Two magnetic fields, the one that we just made by the moving charge and the one that was already there, the permanent magnets or whatever, they interact with each other to apply a force on each and every electron. And if each and every electron experiences a force, so does the wire itself. In fact, it experiences a force in the same direction as the force on each of these electrons. So if all these electrons are moving through the wire like this, and they experience a force downward, then the wire itself will experience a force downward. We're going to learn in a minute how to actually find the direction of that force, and in addition to that, the magnitude of that force. Let's deal with how to find the direction of the magnetic force first. Now, this requires us to use another hand rule. Remember, the first hand rule that we learned was called the wire grasp rule, and that one said, stick your thumb in the direction of the current, and your fingers will automatically, when you bend them, point in the direction of the magnetic field. The second hand rule that we learned yesterday was the coil rule. And the coil rule was opposite, right? Remember when we had a coil of wire or a solenoid, we said that we would stick our fingers in the direction of the current and our thumb would point in the direction of the magnetic field inside the coil. This time, this rule is going to be a fair bit different than either one of those rules. The third hand rule, or the hand rule for deflection, requires us to put our thumb in the direction of the moving charge or in the direction of the electric current. And remember, we always make our thumb and fingers perpendicular to each other, so we never put them like this, right? I don't want my thumb to be with my fingers. I want it to be perpendicular to my fingers. So my thumb is going to point in the direction of the moving charges or the direction of the electric current. My fingers this time that are straightened out, not bent, not curved, like they were in the last two hand rules. This time they're straightened out. And they're going to point in the direction of what we call the external magnetic field. The external magnetic field is not the magnetic field that was caused by the moving charge, but rather it's the magnetic field that was already there, the previously existing magnetic field. Maybe it's the magnetic field of the Earth is the external magnetic field. Maybe it's magnetic field surrounding bar magnets, whatever it is. It's not the one that's caused by the moving charges. It's not the Oersted. Remember that 1819 Oersted discovered that moving charges generate magnetic fields? That's not the magnetic field we're talking about here. Now there's a third variable in this one. It's the palm of your hand. Your thumb points in a certain direction. Your outstretched fingers, your straightened out fingers point in another direction. Your palm will automatically point in a certain direction, and that direction is going to be the direction of the magnetic force. Now this hand rule only works if the wire is perpendicular to the field. So if they're not perpendicular, you can't use the hand rule. But the good news is this. If they're perpendicular, you can use the hand rule. If they're parallel, you can't use the hand rule. But the good news is the force is zero. And if the force is zero, you don't need to find the direction of it, right? There is no force. If you got a magnetic field pointing this way and a wire going this way, there is no force on that wire. There's no magnetic force on that wire. So there's no point in having a hand rule to describe that if there is no force. If they're not perpendicular or parallel, well, then it becomes a little bit trickier, but the good news is we don't have to deal with that in Physics 30. So the only two situations that you'll see are the wire being parallel to the field. That's the easy one. Hope and pray for that one because the force is zero and there's nothing to do. Or they'll be perpendicular, in which case to find the direction of the force, you'd have to use the hand rule for deflection. Thumb the direction of the particle, fingers field, palm points in the direction of the force. Okay, everybody take out your hands. Shake them. Do a little shaking of the hands. Get them going here. What about the magnitude of the force now? Well, just like we said in the last situation, the last page, we said if the particle or the wire is perpendicular to the field, there's a force. We can describe that force by the hand rule for deflection or by an equation that you're going to learn in a second. If they're parallel, there is no force. So if they're parallel, don't even worry about it. And if they're not perpendicular or parallel, there is a force, but we don't have to worry about it in Physics 30. Look, if they're parallel, there is no force. Don't worry about a hand rule. Don't worry about an equation. If they're perpendicular, then yeah, you got to worry about a hand rule. It's the hand rule for deflection, but you've also got to worry about a force. The magnitude of that force, okay, we're not going to get the direction of that force from the equation. We get that from the hand rule for deflection. But the magnitude is going to be equal to Q. No, it isn't. Oh, I'm lying. That's another equation. It's going to be equal to I. You guys know what I is, right? I is electric current in amps, coulombs per second. L, what do you think L stands for? What's L? Yep. Yeah, it's the length of the wire, but you've got to be careful here. It's the length of the wire perpendicular to the magnetic field and the portion that's in the magnetic field. So in other words, if you have, I don't know, 2 meters of wire and only 1 meter is actually in the field and the other meter is not in the magnetic field, then it's only the 1 meter that we care about. It's the portion that's in the magnetic field and perpendicular to the magnetic field. If I had a magnetic field like this, and I had a wire like this, then it would only be this portion of the wire that I would care about. Because this portion is parallel to the field, and there is no force on that portion of the wire, and this portion of the wire is not in the magnetic field, so I certainly don't care about that one. the portion that's in the field and perpendicular to the field. And finally, our last variable is B. That's the magnetic field strength. I mentioned to you guys a few minutes ago that this equation is really what we call a cross product. You're not familiar with the mathematics of cross product. We're simplifying it to make it work for the specific situation of a charged particle being perpendicular, of the wire being perpendicular to the field. Because of that, we're going to change it from a cross product to a regular product, but we are going to add a little symbol. What do you think that symbol means? A little upside down T. The real equation is I times L cross B, but we're simplifying it to make it I times L times B, but we got to make sure that L and B are perpendicular to each other. So that little upside down T just is a little reminder that this equation is valid if they're perpendicular to each other. Does that make sense? So you want to find the direction, use the hand rule for deflection. You want to find the magnitude, then let's use ILB. That is if they're perpendicular. If they're parallel, don't worry about it. If they're not perpendicular or parallel, well, then you're in your first year university. And we'll let your professor teach you about that. It's not actually all that hard, actually, but we don't have to do it, so we won't. All right? So we'll get example 2 that's on the handout that I gave you earlier. This is a 10 centimeter long wire carrying electron current into the page. Electron current just means that we're talking about a left-hand rule here, right? If it was positive particles, it would be a right-hand rule. Now, in the context of wires, can you ever really have positive charge moving? Not really. But every once in a while, I would say less than 5% of the time, you see something called conventional current. A 10 centimeter long wire is carrying conventional current. Conventional current means the flow of positive. It doesn't really happen that way, but sometimes you still see it listed. Not very often, but every once in a while you do. If they say positive or conventional current, that's okay. Just use your right-hand rule. Okay, even if you don't like it because it's really negatives that are flowing, that's okay. Just play the game and use your right hand for it. This isn't conventional current, though. This is electron current. It's directed into the page. There's a magnetic field pointing towards the left of the page. So picture this here now, guys. We have a current going into the page. We have a magnetic field that's pointing to the left of the page. Man, I wish those were parallel to each other. Why do I wish they were parallel to each other? That doesn't happen very often either, but why do I kind of hope that they're parallel to each other? They wouldn't have to do anything, right? Because there is no force if they're parallel to each other. Are they perpendicular to each other? Yeah, they are, right? One's into the page, one's towards the left of the page. So I'm allowed to use that hand rule for deflection, and I'm allowed to use that new equation that I just learned. This many electrons flow through in 10 seconds. What's the magnetic force acting on the wire as a result of the field? Let's find the magnitude first. Let's say F is equal to ILB. But we don't know what I is. How do we find that? Q over T. We just did that a few minutes ago, right? Q is 8 times 10 to the 19. No, it isn't. Oh, look at that. We don't even know what Q is, do we? Boy, there's more to this question. How do you find Q? Same way as we did in that other example question, right? We say 8 times 10 to the 19. That's the number of electrons times the charge of one electron. That gives us a number of electrons that is equal to, do you have it? 12.8. Okay, 12.8 coulombs, not a number of electrons, but rather a total charge. 12.8 coulombs, which we're going to divide by the time, which is 10 seconds. which is 1.28 coulombs per second, or amps. And then we're going to say 1.28 amps times the length of the wire, which is 0.10, times the magnetic field strength, which is 0.02, gives us a force, or at least a magnitude of the force, of 2.56 times 10 to the negative 3. Yep. For a charge. Let's just double check that. 8 times 10 to the 19 times, should be 10 to the 19, I think. Oh, yours says 14? Okay. Why does mine say 19 and yours say 14? The wisdom of Dawson. All right, so you will get a different answer then. If yours says 10 to the 14, okay, if yours says 10 to the 14 on the sheet that I gave you, let's see what we get here. 8 times 10 to the 14 times 1.6 times 10 to the minus 19 gives me a value of 1.28 times 10 to the minus 4. Which we're going to divide by 10. Which gives me I think that should give me 1.28 times 10 to the minus 5, which we're now going to multiply by L times B. So now let's say 1.28 times 10 to the minus 5 times 0.1 times 0.02, 2.56 times 10 to the minus 8. Is that what you get there? Okay. Oh, what do you got for the magnetic field? Sorry? It just doesn't have the number? All right, we'll make it 0.02. Well, I don't know what happened there. Brutal. Okay, there's the magnitude of the force. What about the direction? Negative particles, so we use our left hand. Remember, it's not the wire graspable. If we wanted to find the direction of the field caused by the moving charges, we could do that, right? Thumb, bend your fingers. The magnetic field caused by this would be counterclockwise, but that's not what we're trying to find. It is that magnetic field, though, the red one, that interacts with the blue one to cause the magnetic force. The magnetic force we're going to find by using the hand rule for deflection, which says thumb in the direction of the particle, which is into the page. Fingers point in the direction of the field, the external field, which is towards the left side. Thumb points which way? Or, sorry, palm points which way? Be careful, don't say down. Let's say towards the bottom of the page or down the page, okay? Because for me, it's down, right? But for you, if your page is horizontal, it would be towards the back of the room. Any way you look at it, it's down the page or toward the bottom of the page. All right? All right, let's have a look at worksheet number 13. Going to have you work on, just keep working on the questions here, worksheet number 13, and in a little bit we'll stop you and we'll do 1 or 2 questions as practice. Okay, we're going to have a quick look at question number 3. It says, calculate the initial acceleration of a 50-gram, 20-centimeter length of wire that carries a current of 0.6 amps if it's exposed to a magnetic field of 0.5 Tesla. Now, this magnetic field must be perpendicular to the electric current in order to have a force, in order to have a force that we can calculate at least. So we're going to assume that it is, but remember that a question should state that, and on a test or a quiz or an exam it would state that. I circled grams, I circled centimeters, because I don't want to forget to convert those to the standard units here. Do you guys remember what to do in Physics 30 if you're asked to solve for acceleration, like 99.9% of the time? What needs to be with you? To get acceleration, the force needs to be with you, right? But this time it's not an electric force like it was in the last unit. This time it's a magnetic force. So let's get that. The magnetic force acting on this wire, assuming the wire is perpendicular to the field, is ILB. I is 0.600 amps. L is 0.200 meters, and B is 0.500 Tesla. So we multiply those together, we get a magnetic force of, what's that going to be, 0.06, is that right? 0.06 newtons. Now we're not done, because that's just the force. Now how do you find the force? Sorry, how do you find the acceleration once the force is with you? A is equal to F over m. And the mass of this wire here is 50 grams or 0.050 kilograms. So remember that it's like, it's Jedi school, it's Jedi training, right? The force needs to be with you. Well, the force is with you. Once you get the force with you, okay, this is what you really need Jedi training for. What do you do with the force? Okay, you got to be able to do something with the force. Okay, may the force be with you? Yeah, big deal. The force is with you. What do you do with the force? Well, we have to divide it by the mass to get the acceleration. And when we do that, we should get, I believe that's 1.2, isn't it? Anybody have that? I'll check my answer sheet here. Yeah, 1.2. We could say meters per second squared, which usually we use for acceleration, but we could also say newtons per kilogram. All right, I'll give you a couple more minutes to work on the rest of those questions. Question number 5, we're going to do now. It says, calculate the mass of a 20 centimeter long suspended wire. It's suspended. That's a big word for us. When we see the word suspended, we see the word hover, we see the word balance. Okay, we pull out our little imaginary physics thesaurus, and we look at words that mean the same thing as suspended. Okay, suspended means balance forces, always. Okay, if something's suspended, balance forces are what we're going to do. It always means exactly the same thing. Well, what two forces are you going to balance here? Generally, one of those forces that you're going to balance usually is going to be gravity, certainly if it's in the Earth's gravitational field. Now, occasionally, given another context, you might balance magnetic force with an electric force, but usually it would be a gravitational force with something. Never balance fields, by the way. You always want to balance forces. What is the other force that we're dealing with here besides gravity? Gravity gets balanced with the magnetic force. So we're going to say Fg is equal to Fm. And then we're going to say m times g is equal to ILB. That's assuming that the wire is perpendicular to the magnetic field, which should be stated, but we have to assume here. Let's solve for the mass here. M is equal to ILB divided by the mass here. So I is, what do we got here? 0.100 amps times the length of the wire that's in the magnetic field. That's 0.200 Tesla. Oh, sorry, meters, that is. The magnetic field is 0.3, 3 times 10 to the minus 1, and we're going to divide that by the mass, which is, sorry, that's wrong. Divided by g, right? Nobody was going to stop me on that? Divided by g, which is 9.81. And when I do that math, that should be pretty easy to do in our calculators. We get 6.12 times 10 to the minus 4. Is that okay? Okay, not bad, eh? I want to take a look at an application of this thing that we just learned about magnetic force on a wire, which, remember we said when we started the whole interaction between electricity and magnetism, we said that the discovery that electricity generates magnetism is probably, at least in my mind, the most important technological discovery in the history of the world. We're going to learn to describe to explain an electric motor here today, a DC electric motor. Now, understand that it relies upon what we just learned, that a wire that carries a current in a magnetic field experiences a force, but ultimately that still goes back to that Oersted discovery, because if you didn't have the wire generating a magnetic field, there would be no force. So even though it kind of looks a little bit different, and we're not talking about it in the context of Oersted's discovery, it still fundamentally goes back to that discovery. Here's how the electric motor works. You've got a power supply here, and that's labeled a negative and a positive side of the power supply. You get electrons leaving which side? Side 1 or side 2, the negative or the positive? Which way do electrons go? Clockwise or counterclockwise? Clockwise. So electrons are going to go this way. They encounter what's called a brush. Now this brush is touching, this is a little black part right here. This brush is touching, but not connected to, not welded to or attached to this round thing that we call a commutator. Specifically, it's actually called a split ring commutator. This commutator, while touching the brush, is connected to or is attached to this thing that we call the armature. So what happens here is that electrons flow around like this. They flow through the brush that is usually made out of copper. Okay? Usually it's made out of copper-like fibers. Like it would be like a hairbrush, except copper wires. Okay, that's rubbing up against this commutator, making an electrical contact with this commutator. Electrons will continue to flow through the commutator, through the armature around like this, clockwise, like this, back to the to the commutator, and then back through a brush on the other side, and then back to where they started. So what does this end up doing, though? Well, we know that this wire right here, this armature, that we're going to label A, B, C, D, experiences a magnetic force. In fact, in two places, it experiences a magnetic force. You've got a current going from A to B. The current going from A to B. We'll call that length AB. There is a current that's going, well, it's hard to describe this exactly because it's in 3D, but we'll try. It's going more or less into the page. A magnetic field that goes from north to south. If we say thumb in the direction of the particle, fingers field, palm points up on it. So there's a magnetic force that is up on wire AB. Does that make sense? At the same time, if we do the hand rule for deflection from C to D, we don't have to do it from B to C. How come? Because it's what? Because it's parallel to the field, right? But from C to D, we'd say thumb in the direction of the particle, which is kind of out of the page, fingers field north to south, palm points downward. So you get a magnetic force upwards on AB. Here, let me label this paper that I have in my hand here. Can you guys see AB here? You get a magnetic force upwards on AB, right? Thumb, fingers, palm points up, but you get a magnetic force downwards on CD. Thumb, fingers, down. So that creates what we call a torque. Torque causes rotation. So we rotate about an axis. AB goes up, CD goes down, and what happens to the armature? It rotates like this. Make sense? Now, when it rotates 90 degrees, I want you to notice what happens here. When it rotates 90 degrees, this little split in the split ring commutator actually makes contact with the brushes. So electrical contact is now broken. So it does this. It rotates like this, a quarter of a turn, and then the electric current stops. There's no magnetic effect. But because it has a little bit of inertia, we call it rotational inertia, it keeps spinning a bit. Now look at where ABCD is. Okay, when I flip it over past 90 degrees, AB is now over here on the other side. Make sense? Right? It was AB, flips over, now AB is on this side. Now the current doesn't go ABCD anymore, ABCD, like it is right here. A, B, C, D. The current goes DCBA. Make sense? Well, now let's look at the force on the wire DC. Thumb, fingers, palm points up. BA, thumb, fingers, palm points down. So now DC, which is now over on this side, DC experiences a force upwards and AB experiences a force downward. So you see this, right? Let's go back to our original here. A, B, C, D, AB up, DC down, spins 90 degrees, no current, but it keeps spinning a little bit because of inertia, makes contact again. Now the current goes DCBA, DC gets pushed up, AB gets pushed down 90 degrees. What happens? Current is broken, current goes back ABCD, AB gets pushed up, DC gets pushed down, and so on. So what ends up happening to this? It ends up continuously spinning in the same direction. Now, that's an electric motor. Okay, that's the motor that's in your electric drill. That's the motor that's in your electric toothbrush. Okay, that's the motor that's in your Mixmaster when you're baking cookies. That's the motor that's in the fan that blows the warm air out on a cold morning in your car. Okay, that's the electric motor that's in your electric car if you happen to have a Tesla or hybrid car. That's the electric motor that's in the fan of your computer. Okay, that's the electric motor that's in, in literally millions of different devices. But we know that all electric motors spin at different speeds and can carry different loads, right? Can provide different torques. Tell me one thing. Actually, tell me two things. No, actually, tell me three things. Three things that would make this electric motor of mine spin faster. Let's say you're brushing your teeth and your dentist said, last time you were talking to your dentist said, you're really not doing a good enough job. You need a better toothbrush, but you're too cheap to go out and buy a new electric toothbrush. What are the three ways that you can make your electric toothbrush spin faster? What's one? Increase the current. Yeah, increase the current. If you make the current stronger, the magnetic force on that wire, on AB and on CD, is going to be bigger. So increase the current.
Increase the magnetic field.
Increase the magnetic field strength. So stronger magnets, stronger permanent magnets, right? Okay, you increase the magnetic field strength, you're going to increase the force on those wires, and therefore you're going to make it spin faster. What's the other one? What's the third one? Increase current, increase magnetic field strength, increase the length of the wire. And the way that you normally increase the length of the wire would be to do something like this. Here's one wire. Loop it around like this. What happens every time I loop it around? Yeah, I basically double it, right? I'm doubling the length of the wire. Now remember, this part doesn't matter because that part's parallel, right? But now I have 3 loops of wire, so I end up having 3 times the length, which, if you look at your equation, ends up meaning that we have 3 times the magnetic force. So it's going to spin faster, right? Make sense? All right.